Hi, I'm Hao Qi, and today I will introduce a paper called Strong Coupling of a Single Electron in Silicon to a Microwave Photon. And actually, this presentation has some problem because I found MacBook cannot record the pen and laser point in the PowerPoint show. So this may cause some confusing to you, so sorry about that. So here, let's first talk about the motivation and background. So actually, as you know, the long-range interaction between qubits is very important for the quantum computation network. And for the long-distance interaction, the optical photon is a good carrier. While for the on-chip interaction, the microwave photon is a better choice. Actually, if you can realize this strong coupling between microwave photon and this double quantum dot system, this will be a big milestone for the quantum computation network. And actually, secondly, the motivation is that a second motivation is that we can fabricate such hybrid superconducting quantum system by using this strong coupling and use both the advantage of the superconducting qubit and the advantage of the quantum dot qubit. But here we have a universal challenge based on the previous work. Actually, the strong coupling means that the coupling strength between the quantum dot and superconducting qubit is larger than the dissipation rate of the superconducting cavity mode and the quantum dot mode. But the charge noise is very large for the double quantum dot system, which means the dissipation rate cannot be suppressed. And actually, in this paper, the paper proposed such silicon-silicon germanium hydride structures and the new overlapping gate architecture to allow them to suppress this kind of dissipation rate, and which enables them to realize such strong coupling. In some past relevant work, actually in 1992, the atom can coupled with cavity is already proposed and experimentally realized. In left figure, you can see the cavity consists of two mirrors M1 and M0, and the atom CCS beam is input from top to bottom. And when the CCS atom is in the cavity, you can see the strong coupling by see the spectrum. And actually, in the spectrum, you can see the mode splitting. And the quantum dot coupled with cavity is already experimentally realized in 2004 in the middle figure. Actually, I think this work is very elegant. You can see the cavity is composed of it consists of two Bragg reflectors on the top and bottom part, and in the middle of this cavity, the quantum dot is fabricated, and as a result, this quantum dot can strongly coupled with this cavity mode. And for the double quantum dot coupled with superconducting cavity, Petter also has already done a good job. Petter's group in 2012. Actually, at that time, they coupled this indium arsenide double quantum dot with this superconducting cavity. And here, after realize the coupling between the indium arsenide quantum dot with such superconducting cavity mode, they do this in the silicon platform. So figure A is their superconducting circuit picture, and in the right circle is a double quantum dot. And figure C is a zoom-in picture of their double quantum dot. You can see S, B, and P are three electrons on top of the quantum dot. And P2 is connected to the cavity, and P1 is another microwave input port. So figure D is another sketch map for such quantum dot. So the electron is confined in the quantum well, and the quantum dot is defined by the electron on top of the structure. And after the fabrication of this, they mirror the transmission spectrum of their cavity. You can see when the microwave photon is on resonance with their cavity, they will see a peak on the transmission spectrum, and the dissipation rate of the cavity, kappa, is about 1.0 MHz. And after characterizing their superconducting cavity, they characterize their double quantum dot system. And figure A is their can show us the characterize of the double quantum dot system. So this figure can understand like this. For each VP1 and VP2, you can draw a set of energy level diagram, and the lowest energy level is the most stable energy level, and which is drawn in this figure. And this pair of numbers describe the number of electrons in both quantum dots. For example, 1, 0 means that one electron is in left quantum dot and 0 electron is in right quantum dot. And there is some interesting thing happening at the transition between the two elements, as shown in figure B. Actually, figure B is a transition between 2-3 energy state and the 3-2 energy state. And from bottom to the top, one electron from the right quantum dot tunnel to the left quantum dot. And actually, in this coupling region, the electron delocalize, and the two new hybrid quantum system, quantum energy state will show. Actually, this can be described by solving the Hamiltonian eigenfunction. So if the two energy eigenstate is far detuning from each other, because of the energy conservation condition, they cannot couple. As a result, here you can write the Hamiltonian eigenfunction as H0 phi is equal to E phi, and you can solve two energy eigenstates phi 1 and phi 2, and also solve the energy eigenvalue E1 and E2. But when the energy of the two quantum states get closer and closer, because of the perturbation, they can couple with each other, which can be described by matrix T. And now the new Hamiltonian can be written as the addition of H0 and T. And you can solve the new Hamiltonian eigenfunction and get two new hybrid energy eigenstate psi S and psi A correspond to symmetric eigenstate and antisymmetric eigenstate. And you can also solve ES and EA and find the frequency difference Fa now. And in the energy level diagram, you can see instead of crossing with each other, the energy level diagram shows such anti-crossing phenomenon, which means they are coupled. So here we show the coupling between two quantum dots. But actually, if the microwave photon is approaching this frequency difference, the microwave photon can also coupled with this qubit mode, which can be described by the GC model. Actually, HA, HC, and HINT are three Hamiltonians describe the qubit mode, the cavity mode, and the dipole interaction term. When the qubit mode and the cavity mode are far detuning, in the top figure, you can see they are not coupled with each other. But in the energy level diagram, when the frequency difference between the qubit mode and the cavity mode gets smaller and smaller, you can see the strong anti-crossing phenomenon happens in the middle and bottom figure. Actually, if you see the transmission spectrum, you can see instead of one dip in the uncoupling condition, you can see two dips in the coupling region. Actually, this phenomenon can be easily explained by the Heisenberg-Langevin equation of motion. And here I will not explain this equation of motion in details, but only describe some concept here. You can write the Hamiltonian of the total system in the rotational frame as H total. And we can assume that the double quantum dot, the excitation of the double quantum dot is very low. As a result, the sigma z is about -1. And we can write the Heisenberg-Langevin equation of motion for A and sigma minus. Actually, this is the Heisenberg equation of motion, but add some dissipation term. So for the equation of motion for A, we can see the dissipation term kappa over 2 multiply A, and the square root of kappa 1, A in 1, is an input term because of the microwave input. And AN2 is a noise term because of the part 2. And the same for sigma minus. Gamma over 2 sigma minus is a dissipation term for the qubit, and F is a noise term. And if the microwave input power is very large, we can use the number alpha instead of input operator AN1. And from the input-output theory, we can also write A out 2. And for the steady state, which means that the dot of A and dot of sigma minus is equal to 0, we can solve the A out 2, and we can get the transmission of the cavity T, which is equal to the square of the A out 2, and the phase response, which is equal to the phase of the A out 2. And then we can draw the spectrum or transmission spectrum. And also, instead of deeply analyze the equation of motion, I want to analyze this spectrum simply by considering the unresonance condition. So for the uncoupling region, when the microwave photon is unresonance with this cavity, you will see a dip in the transmission spectrum. Well, when the double quantum dot is coupled with this cavity, the photon in the cavity can be absorbed by the quantum dot and then emitted, but get an additional phase. And because of the additional phase, the unresonance condition is broken, and as a result, you cannot see the dip in the middle of the figure. And actually, experimentally, they also see the phase response of their system as in the left figure A and B, and this can fit very well with our theory, Heisenberg-Landau equation of motion. And also, they observe the vacuum Rabi splitting in the right figure A and B. You can see for the far detuning region, epsilon is equal to 6. The qubit and the cavity is hard to coupled, and as a result, in the transmission spectrum, you will see one peak. And if epsilon is equal to 0, they can couple with each other. As a result, you can see a mode splitting, and this splitting is equal to 2 times the coupling strength. And actually, this can also be calculated by using the theory as we derived the coupling between the double quantum dot system. They are the same, so here we will not repeat the same procedure. And some summary and discussion. So here, the author fabricates such silicon germanium low charge noise devices, and their coupling, their dissipation rate to gamma can be 5.2 macros, which is 2 or 3 orders of magnitude lower than the previous work. As a result, by using these devices, you can realize the strong coupling and vacuum Rabi splitting. And this work can pave the way to the silicon-based quantum processor and such hybrid quantum system. But some discussion, actually I think even though the gamma is 2 or 3 times lower than the previous work, the coherence time is still low. And actually I noticed one interesting thing is that in the introduction part, the author note that the coherence time for the silicon platform can exceed several seconds. But in his reference, the work something about the defects in the phosphorus doped silicon platform rather than this double quantum dot system. So I think this dissipation of this double quantum system can still be a huge problem in the future work. Okay, thank you for listening. That's all.